tries to eavesdrop, and she doesn't know what polarization Alice is using. Alice is randomly switching between these two modes. Okay? Eve doesn't know. So Eve is also trying to guess like Bob. Okay? Eve tries to steal a photon from Alice. Okay? And then after she steals a photon, decides on its polarization, and she will take the same polarization and sends it to Bob. What would happen in that state? You know, that one way is that you can think of that you have a polarizer. The polarizer might be something like this, and then you send a photon in, and then Alice might be over here. This is a prismatic polarizer, and then Bob might be over here. Okay. Trying to receive, these are prisms, okay, you can align the polarization of the photons by adjusting some of these things over here. And then Alice tries to steal a photon, maybe by interfering the experiment with another deflector so that some photon goes to her. And then do some experiments over here and then beam back another photon and then try to send it to Bob. Okay? And she will also receive this photon with a certain polarizer to decide on whether it's vertically or horizontally polarized. And after that, she sends it back to the system. So what happens if Eve tries to do that? If Eve tries to do that, then she's like Bob in the first position. 50% of the time, her polarizer is aligned with Alice. 50% of the time, her polarizer is misaligned. Okay? And then, say, previously, Alice and Bob knew that 50% of the time, their polarizers were correctly aligned. Okay? But out of this 50% of the time, Eve is going to steal some of those data. Eve is going to steal that with a random polarizer. Eve actually does not know what polarizer the photon she has. Okay, she will only be half right in deciding the polarization of these correct photons that were correctly transmitted between Alice and Bob. Okay, she will only be half right. And then she sends them back. So the photons that she sends back to Bob by this interruption procedure will corrupt half of these photons. Okay. Now then, if Alice and Bob checks their data on this correct transmission and found that they are half wrong, we will suspect that there's an eavesdropper who has intercepted the photons and retransmitted them. Okay, then that's how you make this system secure, interference proof. Nobody can intercept your photons. And also no cloning theorem. Alice cannot clone this state of the photon that comes in and then transmit in exactly the state of the photon, say if the state of the photon happens to be one of these two states that Alice is transmitting. Eve cannot clone that state and transmit it back to Bob. Eve has to decide on whether it is one of these two states or one of these two states. Okay, depending on whether she's using a 45 degrees polarizer or H and V polarizer. So she will corrupt this data. She will corrupt this data. And Alice and Bob can check and say, over the phone, I know that over this instance of transmission, our polarizers are correctly aligned. Our data should be correct. And if they found that even when the polarizers are correctly aligned, the data was wrong, then you know that something is happening. So they have to stop transmission and go looking for Eve. Okay, do a manhunt or woman hunt for Eve. Okay. So, do you understand this? So it's quite easy to understand, okay, quantum cryptography. And apparently, this kind of system has been implemented for real-world applications so that it can be actually used. There's a name for this kind of transmission. BB84. scheme. It was done around 1984 due to Bonnet, Bennett, and Brasak. 1984. Okay. And you can use this to transmit secure information. But this will not work if you have a classical scheme. If you have a classical scheme, and if Bob and Alice are communicating with each other using zillions of photons, it doesn't matter if Eve steals one of the photons. Okay, maybe Eve steals 5% of the photons and found that. Well, if the polarizer is vertically polarized, most of the photons will be vertically polarized. I steal 5% of it and transmit it back to Bob. Bob wouldn't know. Okay, it's just a small percentage. But it is this linear superposition of two states that not allow anybody to steal the state of the photon. Okay. Are there any questions on this? If not, then let's move on to how we do quantum computing with this kind of strange things that we have with quantum mechanics.
Is there any way for Eve to couple the light instead of just taking it away? Isn't that coupler? Is there any
Coupler?
The couplers in like
Coupler?
couplers. Is that something similar in optic you can use?
Using a light coupler?
Yeah, instead of taking the photon out and then changing it, just not change anything, just have a very small version of that.
Yeah. Yeah, you suggest that Eve uses a coupler and couple a photon out and then look at the photon and transmit it back. So if she does this, the coupler, that means that she will not receive a photon 100% of the time. She will not intercept Alice 100% of the time. Say if you have a coupler, say if you think of a coupler, maybe you can have a prismatic coupler here, and then the light comes in, I don't know, get the wave to bounce around like this. The photon bounces around and emerges, and then maybe sometimes the photon bounces out here. That's what you do in optical coupling, right? You use a prism, do some sort of optical coupling. Or maybe there's a gap here, I don't know, you might need a gap here. And the photon will not emerge 100% of the time. It will emerge only sometimes because of the probabilistic interpretation. If there's only one photon coming through this channel, certain percentage of the time the photon will go there, certain percentage of the time the photon will go there. So Eve will not be able to intercept this photon efficiently if she uses a coupler. Because coupler has exponential decay. It decreases the probability of a photon detection over here. Sometimes you see, it's like tunneling effect. If you use a coupler, then it's very much like a tunneling effect. If you have light going this way, it becomes exponentially decaying. And sometimes you might have the light going this way after it exponentially decay, but its amplitude is greatly diminished. And you can think of that the likelihood of photon tunneling through this system is greatly diminished. Not always that you will find a photon, but at least Eve wants to intercept the photon decidedly, precisely, and every time that if there's a photon transmitted, she wants to intercept it and collect it, look at the polarization, and then retransmit it. Then she will have to deflect the photon into her lab or her equipment, decide what polarization it is, and then retransmit. Yes?
But if we use a large array of couplers that are somehow synchronized so that we have a higher probability of intercepting most of the photons.
If you use a high array of couplers, so if you have high array of couplers, and then the photon will go into Alice's lab, right? Alice's laboratory, and she has to decide what polarization this photon is. It's no different from a beam splitter. You use a high array of polarizer. What I was suggesting was that maybe Eve would design a beam splitter over here, and then get the photon to be deflected into the equipment, and then send the photon back. After she decided on what polarization, send it back over there. It's no different from the series of couplers that you ensure that the photon will get into Eve's equipment. Eve has to have an equipment to receive the photon and decide on the polarization. Decidedly, okay, 100% what polarization this is, and send it back in order to steal the information from Alice to Bob. Okay, but when she tries to steal this information, she will corrupt it, 50% correct data out there, and then she will be discovered, okay, and hunted down by Alice and Bob. Okay.
How practical is to count number of photons? We can count the.
Well, apparently they can do it now. You can do it at optical frequencies. I'm not very familiar with single photon experiment. There's something that I should read up more about. The simple fact is that h bar omega is large at optical frequencies. It's very hard to do this at microwave. This quantization of energy is a very small effect at microwave, but it is measurable in optical frequencies. Okay, people are doing single photon experiments. And I think Paul Quick in the physics department here does a number of, he's a leader in single photon experiments. If you can measure just 1 or 2 photons at a time, you can actually do a lot of things. Okay? Because you can extract quantum information that is embedded in photons. Photons can be think of as quantum particles as well. Are there any other questions? Okay, let's look at quantum computing then, if there are no other questions. So quantum computing is attractive because of quantum parallelism. Quantum parallelism is very much like sending a whole bunch of soldiers to look for a hole in the Great Wall of China. Okay, so you just need to send one soldier, and he immediately can scan the whole Great Wall of China and find the answer for you. Okay, so let's look at quantum computing. So in quantum computing, we should introduce the concept of quantum bit, which has no classical analog. Quantum bits are also called qubits. So if we design an electronic system, like a flip-flop, electronic flip-flop, and we use that to denote ones and zeros, right? We go through a lot of electronic design, and you have a one state and a zero state in an electronic flip-flop. And that gadget that you design has only 2 states possible, either 0 or 1 state. Okay? But in a quantum bit, what you can have is that you can use a quantum state to denote 0 and 1 bit. Like in the case, we can use a vertical polarization to denote a 0 bit, and then a horizontal polarization to denote the other bit. Okay? But photons are not very good for quantum computing because they zip around at the speed of light. It's very hard to control them. So what people try to do is to use particles like trapped ions, get them trapped in the certain fields. If they're quantum particles, they will have 2 states, and then they can be flipped into 0 state or 1 state and use that to denote the quantum state of the system. And then a quantum state of a system, if you have a 2-state system, like spin out and spin down in NMR, okay, or maybe some of the other things like ions or electrons might be in some 2 states, okay, and hopefully these 2 states are localized, then you can build quantum computing with, not like photons which are zipping around the universe at the speed of light. Then you can use this to denote computing state. These are called qubits. This is 0 bit and this is 1 bit. And the good thing about quantum bit is that it can be written as a linear superposition of these two states, and there are zillions of ways you can combine them. Okay, so if you have a, say in NMR you have a up spin and a down spin, this might represent, I don't know, ones, and this might represent zeros, and then you can have the spin of the proton of the molecule to be a linear superposition of these two states, and this spin can be combined in umpteen ways. Okay, can be combined in umpteen ways. And hence this nuclear spin that you have in NMR, which usually is a proton spin, can have any states by a linear superposition of these two states. Okay? So these are called qubits. And qubits, as you have learned before, can be represented on what is called the Bloch sphere. This state can be, the state of a two-level system can be represented on the surface of a sphere, which is called a Bloch sphere. I think we went through that when we did angular momentum. And then you can have umpteen points on the Bloch sphere that represent this quantum state. You have this sphere, okay, and depending on how you pick 0 and 1, this might represent an up spin and a down spin, and then that spin that you have is pointing in any direction on the surface of this Bloch sphere. There are zillions of states that you can have. And of course the restriction is that due to quantum interpretation that this has to be true. So then the state of a quantum system that has two states only can be represented by these two numbers 0 and C0 and C1. Okay? So we can get this state of the quantum system to change by doing experiment, by maybe align this with the magnetic field and try to get the spin to change direction. Like in MRI or NMR, you try to use the radio frequency pulse to get the spin to go in different direction, and hence you can change the state of the system. And that's what they were trying to do. And the first quantum computing was actually done with NMR. But it's very clumsy because you need big magnets and so on. So people are looking away from NMR system to do quantum computing. Okay? So the basic idea is that these states can evolve, and they can evolve to a different state. And we can define the evolution with the matrix operator M11, M12, M21, M22. Okay, so if the state was initially in the C0, C1 state, you can do experiment to change the state, and you can describe the experiment by this this matrix operator over here. And you can think of that it's very much like operating this time evolution operator on the state side. Okay? And you can think of this as M hat. M hat is given by this time evolution operator. This M11, M12, M21, M22 is just matrix representation of this operator using a two-level system. Okay? So there are a few kinds of gates, quantum gates, that has been defined. And some of these gates have this property that, like the AND gate, the NAND gate, the NOR gate, and the OR gate in digital computing, you can define such gates that if you have a quantum system in this state, okay, if it goes through the X gate, it's like the NOT gate. Okay, it's the negation gate. It just flips the bits around. Okay, zeros and ones just exchange position in this NOT gate. Okay? And then there's a Z gate, And if you have this state coming in, what comes out is that is one of the signs of the coefficient just changed. Okay. So the Z gate is the gate that flips the sign of one of the two bits, okay, one of the two states of the quantum system. And then there's a third gate called the Hadamard gate, H gate, that has this property, that if you have C00 coming in plus C11 coming in, what comes out, okay, is equal to this rather complicated state. Okay, but we have to assume that the quantum state is in coherence. That means this state and this state are in quantum coherence with respect to each other when we do all these experiments. We are not assuming that they are not coherent with respect to each other. They are incoherent, in quantum coherence. So when we design these gates, they have this property. And quantum coherence is retained by this gate that operate on this quantum information. So we can think of this X operator actually is a quantum operator, but its matrix representation is given by this. And that this D hat operator is a quantum operator. Okay, it's one of these quantum operators. This is with slight abuse of notation. Okay, because we are using matrix representation on the right hand side, we are describing this quantum operator on the left hand side. And then the matrix representations of these operators are given by such. Okay, roughly given by this. So if you were to write this explicitly, then you can say x of psi is equal to C10 plus Z01. If you were to write this in quantum mechanics notation, then Z hat of psi is equal to C00 minus C11 for the Hadamard gate with C0 over 2, 0 plus 1 plus C1 over 2, 0 minus 1. Okay. You can also write down the algebraic form for this transformation, but I will not do that. And there's a third gate called a C0 gate, which is used in quantum computing quite a bit. And this has two inputs and two outputs. This gate now that I have denoted has only one input and one output. You can also have a C0 gate that has two inputs and two outputs. And the C0 gate looks something like this. That it has two inputs going into it, okay? And then the outputs are A, and this line over here, this gate over here. And this has the state of B plus A, and this is XOR operation or modulo 2 addition. What I mean is that if B is 1, A is 1, this gives you 0. Okay? If A is 1, B is 0, it gives you 1. 0, 0 is equal to 0. So it's like modulo 2 addition. Okay, modulo 2 addition or exclusive OR. Okay? So you can actually look at the behavior of this gate, and you should have this kind of matrix representation, that if I were to align all the inputs A, B, okay, the input it can be written this way or that way. Okay, I can have all possible inputs of 0, 0, 0, 1, 1, 0, 1, 1. Okay, these are all possible inputs that I have in this C0 gate. So I can align all these possible inputs in the column vector. Okay, I can align this in the column vector 0, 0, 0, 1, 1, 0, 1, 1. Okay, ask me what kind of matrix I should have here. And then what is my output? Okay, or I can put my output over here. Okay, so I can go through one by one. So if I have a 0, 0 as an input, 0 here, 0 here, I will get 0 here. I will get 0 plus 0. What do I get? If I have 0, 0 as an input, I will get 0, 0 as my output, right? So this must be 1. So the first line of the matrix would be that. Okay. If I have 0 and 1, 0 and 1 as an input, 0 here, 1 here, 0 here, 1 here, and then 0 here. 1 plus 0 is 1. Okay, so I will have 0 and 1. So if I have 0 and 1 here, I will have 0 and 1 as my output. So the second line must look something like this. Right? And then if I have 1, 0, 1 here, 0 here, I will have 1 here, and then 0 here, and then 1 here. Okay, what do I have? 1, 0, 1, 1, right? So I should have 1, 1. Then I should have this as my output. Okay? What? No, I have to align it so that this always appears to be that way. So this will go to be something like 1, 0.
It should be 1, 1, 4, 4, and 1, 0, 4, 4.
No, I have this to be like that. Okay? So if I have I should have 1, 1 above, that's right. I should have 1, 1 above. So I should have 1, 1 here as my output, and that matrix system can be written as such. Okay? So now I have 1, 1, 1, 1, it should be 1, 0, right? 1, 0, I should have 1, 0 out. And then I could write this as 1, 0, 0, 0. So the matrix system looks something like that. Okay? So this is the C0 gate, and it's used in quantum computing as well. And when we write this state, we actually assuming that these are in quantum coherence. It's very important. Okay. Let's see if we can go through a simple quantum computing algorithm. So we can go through a simple quantum computing algorithm for the Deutsch algorithm. Okay, and let's see how this thing works. Let me use that part of the blackboard. I have more space over here. And I have a Hadamard gate for this algorithm. Okay, this is Deutsch algorithm. It's a very simple quantum computing algorithm. Another Hadamard gate here. And then I have two inputs, 0, Q1, the first bit is 0, the second bit is 1, okay, going to this Hadamard gate. And then this state I will call X and Y state. Okay, and it goes through a unitary transformer, unitary operation, UF hat. And then over here I get X. Things remain unchanged, but down here I get Y modular addition f of X. Okay? And then I put this through the Hadamard gate, and out come the thing. And I trace this quantum state. Over here, I call the quantum state to be psi 0. Over here, I call the quantum state to be psi 1. And over here, I call the quantum state to be psi 2. And over here, I call the quantum state to be psi 3. And by all this are happening, I'm assuming that these two states are coherent with respect to each other. They're in quantum coherence. Okay? So let's trace the quantum state through these operations and see what happens to it. So let me assume that in the input, to start with, I have this quantum state, 0 and 1, and in quantum coherence with respect to each other. And then put them through the Hadamard gate. Hadamard gate, as you can see, performs this kind of operations on the two states. Okay? And it will just, this kind of operations on the two states. Okay, so the zeros and one states will become affected. So X will be equal to H hat Q1, okay, will be plus 1. Let's see if this makes sense. So what happens is that I only have the 0 bits coming in here. Okay, I have only the 0 bits coming in there. Okay, then I will multiply by the top row. And then I get a linear superposition of zeros and ones, right? Does that make sense? No, if I only have 0 bit coming in here, if I have 0 bit and nothing here. Okay, so if I multiply 2 times, I have 1, 1, 1, 1, and then I would have 0 bit. If I have only a 0 bit coming here, C1 is 0. So if I look at this equation, I will have 0 and 1, right? So this is still correct. This part is 0, right? So whatever that comes out is given by this. So X is given by that. If I look at this equation over here. Okay? And then Y is H times Q2. Q2 is 1. If Q2 is 1, then it only has C1. I only see this second thing coming out. Okay, so I would have 1 over root 2, 0 minus 1. So X and Y would be in these two quantum states after the Hadamard operation. Okay, then psi 1 is a product state of these two states. Okay, psi 1 is a quantum state at this point. It's a product state of these two states. So I need to multiply these two together. And psi 1 becomes 1 over 2, if I multiply them together, 0 plus 1 times 0 minus 1. Okay, so the product state at this point is given by that. And if you multiply that out, you will get 4 states. Minus 0, 1. This time this is 0, 1. And then plus 1, 0. Minus 1, 1. We're using this shorthand notation that 0, 1 is 0 times 1. Okay, we're using the shorthand notation, so we just consolidate that. So psi 1 is at that state. Okay? So, what happens over here then? What happens over here is that